Welcome to this demonstration of using Autodesk Nastran In-Inventor. During this video, we're going to discuss the benefits of using thermal heat transfer as well as the thermal expansion results to ensure the rotor on this brake assembly will not fail due to high stress concentrations. We'll focus on the rotor by itself and hide the other parts in the assembly. Autodesk Nastran is fully integrated in the Autodesk Inventor application. You will see the Nastran tab in the ribbon, as well as the FEA browser for easily setting up the study in the CAD environment. Let's begin by specifying linear steady-state heat transfer for the analysis type. The material properties can be taken right from the CAD model. The material contains both the conductivity and thermal expansion coefficient for both of the studies we will set up and run during this video. Next, we'll mesh the part or divide it into smaller pieces to be analyzed. For the first analysis, we'll apply the boundary conditions that simulate the heat flux generated from the friction between the brake pad and the rotor, as well as the rate this material releases heat into the surrounding air. All the faces need to be selected, except for the two faces that are coming in contact with the brake pad. We'll input the outside temperature of 293 degrees Kelvin or 70 degrees Fahrenheit. Then the convection coefficient based on the material and ambient airflow. Next, we'll apply heat flux, or the amount of power per square millimeter, for both sides of the rotor. All that is left is to run the solver. This model takes about 1 minute to solve. Let's take a look at the results for temperature. The plot that you are about to see will provide the non-uniform temperature distribution that can be used as a load in the thermal expansion study. You can see some of the heat is transferred to the vanes on the inside of the rotor. We can now set up the linear static study using these temperatures and also apply the torque load as the vehicle comes to a stop. First, we need to hold the part down by fixing the holes where the rotor is fastened to the other parts in the brake assembly. We could use bolt connectors in this case if we included the hub in the analysis. Be sure to watch the video on bolt connectors to see how they work in Autodesk Nastran. Next, we'll apply the torque load on the rotor. We're going to apply the load on the 2 points in the center of the component. Before doing so, let's connect the points to the faces of the part using rigid body connectors. Notice there are two options for rigid body, such as interpolation and rigid. Interpolation works best for applied loads. Rigid works well for prescribed displacements. Now we're ready to add the torque value to the 2 points. We'll apply an extreme load condition of 100 million Newton millimeters, or about 1 million inch-pounds, to both sides of the rotor. Subcases in the FEA browser are a great way to evaluate more than one scenario at a time and compare the results between them. Here we are going to select 3 of them. The first one that you see is analyzing the torque load alone. The second subcase will include the thermal load, which comes from the previous study results. When applying the load, you will see the option to select the result file that was created when the analysis was complete. The third subcase is the thermal load by itself without the torque. After copying and pasting the study, we'll simply delete the 2 load conditions that were copied over. That's all we need to set up the linear static study. We're going to use the same mesh from the thermal analysis. This analysis also takes about 1 minute to solve. Let's take a look at the results using temperature as the only load condition. Starting with the displacement plot, we're observing a deflection of 0.3 millimeters due to the thermal expansion. By showing an exaggerated deformation and animating it, we can visually see how the rotor is moving. Next, we'll find out how that displacement is affecting the stresses in the model. We're seeing high stress in the arc between each fastener, as well as the areas behind the fastener. They are already beyond the yield strength of the material before the torque is applied. Next, we'll look at the stresses with the torque load only. We can see here the vanes on the inside of the rotor are absorbing some of the stress. Finally, let's look at the stresses caused by a combination of the torque load and the thermal expansion. We'll use the same maximum value for the legend as the previous plot, as well as the same visibility settings. Notice the stresses at every other extrusion for the bolts are higher due to the placement of the vanes. Perhaps by adding another vane in between, we can evenly distribute the stress. The changes that we make here in Inventor can be reanalyzed right inside the CAD design environment. There is no need to send the model back and forth between systems. Here we'll simply open the rotor in its own window and change the number of vanes we would like to use. Then, after the study has been run, we can view the updated results for the new design. Looking again at the thermal stress with torque, we can see that the extra vanes in between evenly distribute the stress at each of the extruded bosses for the fasteners. As you have seen, Autodesk Nastran in Inventor helped us to come up with a better rotor without leaving the CAD system. We can now confidently move on to innovation on other areas of the brake assembly.